Hello, everybody. So, as we know, yesterday we have started the topic that is cross section details. So, today I'll be ending this topic. So, that's why I'm calling this topic as a part two because in the part one, whatever I have told, that is specifically related to the wing. Okay, to design a wing, we will use NACA related cross sections. No, so that's why I cover that part separately. mm, to tell about the wing design. So that's why that topic has been kept separately. And here in today's topic, that is in the part two, that is cross section details part two. Here I'll be telling you in detail with respect to the open VSP. Okay. So in our open USP, we have all these cross-section details, that is point cross-section, circle cross-section, ellipse cross-section, super ellipse cross-section, rounded rectangular cross-sections, or rounded rectangular cross-section basics, okay, and rounded rectangular cross-sections behaviors, general fuselage cross-section, fuselage file cross-section, and NACA 4 series aerofoil, NACA 6 series aerofoil, NACA 5 series aerofoil, NACA 4 and 5 series modified aerofoil. That also yesterday we have seen that. Okay, and the NACA 16 series aerofoil. After that, even we have biconvex aerofoil, CST aerofoil, Karman related aerofoil, and airfoil file. If you have that file, even you can choose. Okay, and yesterday, whatever I have discussed, okay, specifically the NACA related aerofoil. So that kind of aerofoil, a complete basic knowledge and other theory of that aerofoil you can get from this source. Okay, that is the theory of wing section, a book by Albert Edward von Danoff and Ira Abbott. Okay, so here we have that book. So by using this book, you can analyze the theory of wing section. Okay, I mean the aerofoil which you want to place for your wing design. So this book is very important because here we have the particular different aerofoil parameters. Okay, and it's easily available in the internet. Just you have to type the name, the same name here. Get theory of wing section by the author name. Then easily you can access that book. Okay, so these are all cross sections what we have in this open VSP that will be going to see in the open VSP. Okay, let me delete all this. Yeah. See, generally, just add any one component like pod or fuselage. I'll separate these two. And next I will take wing also. Yeah, and stack component. Okay, and I'll move this. This components are enough. I'll put on screen. See, in this case, stack case, if I come to the cross section, the type is a pointed type. Okay, and if I come to the second cross section, that is ellipse type, and second cross section, okay, it's a zeroth cross section completely pointed, which means it's closed figure. And first cross section ellipse type, second same, third also same, and fourth again a closed point in this closed. Okay, and in this wing case the cross section what we have, just observe. Okay, see the cross section type, zeroth cross section. Okay, which means here this section, it's, yeah, the cross section type is 4 series aerofoil naka 0010, and again same. Yes, okay, which means here and here the aerofoil is same. Okay, and now I will choose this fuselage geometry, and in this case the cross section what we have, it's closed, we have to close, so that's why it's a pointed cross section type. Okay, and first cross section it's not pointed, it's ellipse type. Second cross section again ellipse. Fourth, sorry, this last, that is pointed, in the sense figure has been closed. Okay, or this geometry has been closed. Okay, and next I will come to pod geometry. In this case only we have design parameter length and finance ratio. Okay, in this pod case with pointed type near leading edge side and trailing edge side. Okay, it's a default thing with only two parameters, length and finance ratio. So whatever I have shown these all things, okay, in this pod geometry, fuselage, wing and stack. Okay, the different cross sections like what we have, the pointed, circle, ellipse, super ellipse, rounded, rectangular, and other cross sections. So here the pointed section what we have, if I talk about this pointed cross section, the point cross section, okay, here what we have, it's under a type section. Okay, so if you drop down in this menu and you can choose a point. Okay, so this cross section, okay, its function is to collect and to close your figure. Okay, or your feature lines, that also you can close. Okay, so all feature lines in a component is the primary method of ensuring the fuselage or stack that is closed. Okay, so here by default, see in this stack case, yeah, currently I have chosen the stack geometry. Okay, so stack, and even we have the fuselage. Okay, these two components have a pointed placed at the beginning and end of the component, right? See, in this case, at the beginning it's pointed, and also at the end it's pointed. And in this case, yeah, and stack case, same. At the beginning it's pointed, and at the end pointed. So this stack and fuselage components have pointed placed at the beginning and end of the component. So that ensures that the geometry are closed. Okay. So point ensures that, or point tells that a closure, okay, fundamentally differs than using a cap on the end of the body. Okay. So that's the use of pointed cross section. And next we have the circle. Okay, see now, if I'll just come to zero cross section. Okay, I'll zoom this component, stack component. Okay, So as soon as I change the point to circle, then I'll get parameter, circle related parameter, that is the diameter or radius. So if I change the parameter, okay, or if I increase the parameter, then you can able to see the change in the geometry, right? So the circle cross sections may here that is a default, okay. Just if you select, then you can get that parameter, okay. I mean, you can change that parameter. So the circle cross sections is a set of diameter at the established location along the body or wing. So you have to note that changing from a cross section with different height and width to a circle will set the circle diameter to an average of these values. And a circle of zero diameter, you see, if I type this circle dia 0 and I will enter, a circle of zero diameter will collapses the cross sections to a point, right? So initially it was with some dia cross sections. So if I type 0 and enter, then that circle, what it was there before, okay, a circle of zero diameter will collapses to a cross section to a point, right? See, you can observe it's completely pointed, and this can be used to close a component, which means for circle we can even convert this into a point, okay. And next we have the ellipse, okay. So in this case, now what I'll do, I'll just select the ellipse. So with respect to this, we got the parameter. So the height and width is 0 0, so that's why you can able to see the preview cross section. It's just a point, right? So an ellipse section has a specified height and width, right? You can able to see the height and the width. So this height and width, okay, uh, this we can alter like this. You can change this height and width, or else if you know your height and width, just type that parameter, ellipse parameter, height and width, and with respect to that, you can able to see the change in the geometry. Initially it was just pointed because of this parameter height and width what we have entered, the dimensionless value, okay. So because of this, geometry also changing, right? Now if I maintain 0, then see, an ellipse of 0 height and width will collapses the complete that cross section to a line or a point like this. One parameter if I maintain 0 and other parameter if I increase, then you can just able to see the line, that's it, okay. If both the parameter maintain 0, then just point. My height I will maintain 0 and width I will increase, okay. You can able to see the horizontal line. And if I maintain width 0 and height increase with some non-dimensional value, then a vertical line you can able to see. And with respect to that, this stack geometry is also changing, okay. So setting both the height and width to 0 will collapse as a point, right? That vertical or horizontal line will get collapsed, and we can able to see just a point. Next we'll go, that is super ellipse. So I'll select that part, super ellipse. So with respect to this, we will get the parameter, that is height, width, maximum width location, m and n. So this cross section, okay, currently everything is 0, so that's why just a point preview we can able to see, okay. Now I'll just disturb the height and width and maximum width location and also M and N. So this cross sectional what we have the super ellipse cross section. So this cross section provides additional control over the shape while limiting the number of driving parameters. So for example, different combinations of M and N. Okay, that exponents can create a circle or ellipse or rounded rectangle or approximations well section type of geometry and other different types. Okay, so altering the location of maximum width, what we have this. Okay, altering this maximum width or maximum w location along with different top and bottom m by n, what we have this m by n exponents. So further the exponents this cross section. Okay, capabilities. So in many cases, a fuselage cross-section can be recreated or at least accurately we can approximate using the super ellipse type of cross-section. Okay, so for many complex sections, a general fuselage type of section, so we will use this type of super ellipse cross-section. Okay, and as per our requirement, we will change these parameters. If I come to fuselage, then you can able to see. Yeah, right. Our fuselage shape will maintain in this way, right? Yeah. So now we'll jump to next. That is rounded rectangle. So this rounded rectangle cross section, what we have after selecting this, we will get the parameter with respect to this rounded rectangle cross section. So here we have the parameters, that is height, width, skew, and keystone, right? So just I'll alter this all parameters of this rounded rectangle cross section. See this key corner, what we have this key corner function of this cross section will enforce the interpolated W lines. Okay, nearest the intended corner to lock into that corner. So thus ensuring a sharp edge if desired. And adding this Q or keystone will alter the true corner radius. You can just observe. And if set such that the sharp corner are enforced, then the radius will automatically return to 0. So many people they use this rounded rectangle for fuselage sections. Okay, See, rounded rectangle completely converted into pointed. Now we jump to next, that is general fuselage. So general fuselage type, with respect to this, we have the parameters height, width, maximum width, location, corner radius, top tangent angle, and bottom tangent angle. Top structure, bottom structure, upper structure, lower structure. So this general fuselage cross section. That okay. If I change this parameter, this is completely similar to the super ellipse. Okay. So here we have the height, width, right? Width, location. So these are all the parameters what we have. Let me set to or by using this parameter we can create a anti-symmetrical top and bottom halves. Okay, if we need, and the additional control also we have. So this additional parameter what we have. So by using this parameter we can do alterations with respect to the top or bottom or upper or lower related strengths. Okay, so this top and bottom angle what we have, this one. Okay, this top and bottom angle we have now, that cannot be altered from zero. Okay, so next we have fuselage file. Fuselage file, in the sense, you can read your file if you have such file. Okay, just choose your file and you can read that file. If not, then just you can increase the width and height. That's it. Okay, so the point will follow a closed path starting from the positive x-intercept and move clockwise about the coordinate plane until returning to a original first point. So the first and the last point what we have here. First and the last point, okay, is the file must be same for the file to work. If we choose from here, and this height and width of this cross section will automatically calculate, and you can even apply your model, that is fx file or fxs file, that is fuselage cross section file. Okay, and next we have 4 series. These are things I already explained yesterday, so I'll not go in deep. Just I will tell the theory part. Okay, in this case, see the NACA 4 series aerofoil section automatically we got, right. The profile we can able to see. So based on the camber, and based on the camber location and maximum camber and thickness to the chord ratio, that all parameter we have based on the functions that defines the shape. Okay, so whatever functions if you give, so based on that function or based on your input value you'll get your profile. Okay, or you can define your shape. Okay, and this naka naming designation will be automatically set according to the convention for this aerofoil. So you may also choose a sharp or blunted trailing edge for this kind of sections. And we also have 6 series aerofoil. Okay, so yesterday when I told about this 6 series aerofoil, naka 6 series aerofoil profile, automatically we got here, right. And here we even change this series 63 to 64, 65, etc., like that. So in this case we have the ideal lift coefficient and the thickness to chord ratio and the functions that specifies the aerofoil shape, and also the aerofoil name will also automatically be altered in the name what we have this. So if you change this parameter, so based on the change in the parameter, the aerofoil name also will get changed, right? See, so you can change your aerofoil name automatically by altering these parameters. Okay, so the 6A what we have, 6A, the 6A series aerofoil, that also will fall into this category itself. Okay, so this series, the aerofoil which will come under this series, 6 series, okay, or 6A series aerofoil, okay, they aim to elevate the sharp trailing edge and cuts that is present in the normal 6 series aerofoil. So you have to know that uh, the A value what we have here, this A value, that indicates the fraction of the chord with laminar flow over the aerofoil. So if you set to 100 or 1 default, you can do that. Yesterday I told about this, right? And after this we have 5 digit, okay, 5 series aerofoil. Okay, so this NACA 5 series aerofoil is automatically generated from the ideal lift coefficient for, sorry, here we have 5 digit. Okay, yeah. So automatically after selecting this type, okay, 5 digit aerofoil, so we can able to see the name NACA 00050, right? So this NACA 5 series aerofoil automatically generated here with ideal lift coefficient. When you can change the ideal lift coefficient as per your requirement, maximum camber location is 15, so you can change that also, and thickness to chord ratio parameter also can be changed. So this all parameter defines about NACA 5 digit series aerofoil. Okay. So additional details about the naming conventions and shape functions can also be found in the theory of wing section. Okay. In this book, additional information you can collect or you can have a look. Okay. The naming conventions and the shape functions and other details you can have a look in this source. Okay, here NACA 4 and 5 series modified aerofoil also we have. Okay, NACA 4 digit and 5 digit series related modified aerofoil. So here we can able to see the modified aerofoil provides additional control over the leading edge radius index and the location of maximum thickness. And the naming conventions follows the usual method for 4 and 5 series aerofoil with the extension of two additional digit indicating these new values. Okay, and the leading edge radius index ranges from 0 for sharp and 9 for semicircular with a default of 6 corresponding to the traditional series. Okay, and even we have the 16 series. So NACA 16 series aerofoil automatically generated here. Okay, with the ideal lift coefficient and the thickness to chord ratio from the functions that defines the shape like this. And this series is subset of the NACA 1 series aerofoil with the location of minimum pressure that is 60% along the chord. Even you can change that also. So the aerofoil naming also can be automatically updated with this parameter. So we have biconvex aerofoil. It's biconvex, yeah, this one biconvex. So the biconvex or opposed arc aerofoil also we can say. So with respect to that, we will get the parameter chord thickness to chord ratio. So this kind of aerofoil we'll use for a sharp-edged supersonic related vehicles purpose. Okay, or we even can say this aerofoil as a biconvex aerofoil or opposed arc aerofoil or sharp-edged supersonic aerofoil. That depends by the thickness to chord ratio and a chord. So these aerofoils are typically very thin, having a relatively low thickness to chord ratio. Okay, and also we have CST aerofoil. So the CST stands for class shape transformation aerofoil or Gulf fan aerofoil. The other one more name of this class shape transformation aerofoil or CST aerofoil is Gulf fan aerofoil. So these are similar to aerofoil shape itself. So that are defined by parameterization of the upper and lower curves. Okay. So in most cases, users will likely begin with the designed aerofoil shape and then they will use the fit CST features just to choose degree to approximate that shape or to change the um, profile. Okay. So from there, the individual parameter of the upper and lower surface curves may be modified to achieve the desired profile. And also we have the Karman related, okay, or Karman Trefts aerofoil. So this Karman Trefts aerofoil I just select and you can able to see the cross section profile. Okay, so mapping a circle into a aerofoil. Just I'll change these parameters. So the profile which is created, okay, from formally mapping a circle into an aerofoil. So by manipulating the epsilon or kappa and tau parameter, you can change this shape. So these aerofoils are of particular intersect in aerodynamics because not only is the circle itself formally mapped to aerofoil, but the analytical solutions of the flow field about a circle. Okay, so uh, for that case, we will use these parameters as per our aerodynamic analysis. So you remember maybe the source and sink and all, right? So this is related to that. And also we have the aerofoil or airfoil file section. So if you have such aerofoil file section, just read your file and add that. Okay. AF file in the sense aerofoil file. You can read your file. Okay. So this will allow you to browse from the AF or DAT file of your choice. So OpenVSP will spline the point to a generate the aerofoil shape. So by default, the baseline thickness to chord ratio will be calculated and set to the Susan section. So however, you may also alter this thickness to chord if you wish. Okay, and you can create a new aerofoil based on the original profile or based on the original uh, preview. So in this camber line conserves in this case. Okay, and detailed information about AAF file format can be found on the programming tech way. Okay, which means if you have such a program related AF file, okay, which you have created, that file you just read and you can add here. like aerofoil database and all like that. Okay, so this is all about today's topic. I hope everything I have covered. Yes, because these are all things I already told. Wedge and all. Yeah, just the parameter will get Bezier. So just with respect to that, each and every type, okay, each and every type of cross section what we have, if you select with respect to that parameter, you will get, and you just alter, and if you okay with that parameter, then adjust to your geometry. So this is all about today's topic. Thank you to all. Hello.
Okay, thank you, sir.
Okay, okay.